Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Time now to go to our questions. Dr. Chris Smith from The Naked Scientist is here to answer them. Now, Dr. Chris asks Sue, what are your views on climate change, global warming, man-made or natural cycles of the Earth's weather, or what are your views? Chris?
Yeah, this is a contentious issue, isn't it? There are people who, on the one hand, think that there's something in climate change. There are other people who say that the Earth has natural cycles. The Earth has been going through warm phases and cold phases for thousands, if not millions of years, and therefore we're just in another one of those. I think really for me, the evidence came together and crystallised into a bit more of an understanding on this when I went to Australia, because I began talking to a number of scientists there back in 2004 who were working on this, and they showed me some data and presented to me evidence that I hadn't really understood or appreciated before, and that's when I think I became a climate change supporter. And I think that really, reviewing the data, the evidence is unequivocal that we are changing the future and the current Earth. Now, if you think about it logically, you can't expect to change the levels in the atmosphere of a whole planet by 30% of one gas, CO2, because the levels of CO2 have gone up by over 30% in the last 200 years, and they're not to be consequences. Now, the one thing that will definitely happen is that carbon dioxide is an acid anhydride. What that means is that when it dissolves in water, it makes acid. So if you put lots of CO2 into the atmosphere, regardless of whether it changes the planet's weather, it will definitely change the marine environment. It will dissolve in the sea, and the sea only has a limited capacity to buffer, in other words, to soak up without changing its acidity level, the amount of acid in the atmosphere. So the more CO2 that goes into the ocean, the more it's going to become acidified, until eventually the level of acid in the ocean becomes sufficient to make the ocean really become quite acid. And we've already seen the pH of the ocean drop by a couple of decimal points worth of pH points in the last, decades really. And so this is a warning sign. Why it's important is that anyone who's ever had their kettle fur up and has descaled it will have seen the effect that putting a bit of acid on calcium carbonate will have. It breaks it down and turns it back into carbon dioxide. Now, lots of marine creatures make their shells by taking carbon dioxide and turning it into carbonate, which is limestone, and that's their shell. So if the ocean becomes acidic, then many creatures perhaps won't be able to make their shells very strong, and that could spell disaster for them. And that includes things like coral. So climate change aside, carbon dioxide is a very big and serious problem, and we need to take it seriously. Now, what's the evidence that the actual planet is changing? Well, there's lots of it there to be had, and scientists are only just beginning to scratch the surface, but they now understand an enormous amount about what Earth's climate did in the past. And it's perfectly true that the Earth does go through cycles of warming and cooling, and that's been happening for millions of years. But we know what causes quite a bit of that warming and cooling. The Earth wobbles a bit as it orbits the Sun. It doesn't go around in a perfect circle all the time, and as a result, these wobbles bring the Earth slightly closer to the Sun or further away in terms of its attitude towards the Sun, and this affects how much solar radiation warms the Earth or gets reflected off back into space from cold ice caps, for example. So the amount of energy input to the Earth changes from one decade to the next, for example. But taking all those things into account, what we should be seeing now is that the Earth should be going into another ice age. The last ice age was about 10,000 years ago. We should now be going into another one. But we're not. We're warming up. And if you look at what's happened, the Earth's CO2 level is very high. And in the past, when the Earth has been at very high temperatures, we've also had a very high CO2 level. So scientists think that CO2 triggers global warming. The reason being that it basically causes a thermal blanket to be wrapped around the planet, and heat that would normally be lost into space ends up being bounced back in towards the Earth's surface, and this keeps us artificially warm. So instead of ending up in an ice age, the Earth is instead now getting hotter. And so many people who say this is just part of the natural cycle, well, it could be part of the natural cycle, but it's a natural cycle that's now going the wrong way to what it's done for thousands, if not millions of years. So there is cause for concern, and why we're so worried is that the Earth is a bit like an oil tanker. If you have it going very, very fast across the ocean surface, even if the captain puts the ship into full power reverse, it still takes many miles to stop. So if we don't do something right now, and we wait until the changes are thoroughly manifest and we've got serious problems, then it will probably be far too late to throw the ship into reverse, because by then we'll be heading straight for the reef and we will run aground. So it's really important that we understand the processes that are going on and we understand how to mitigate them and how to have a sustainable future without actually potentially wrecking the future of the planet for humans. Because if we want to be here, the Earth will be here regardless of what we do to it. We just won't. So it's if we want to have a future for humankind, we need to take this problem seriously.
Chris, thank you very much. Now, Jonathan in Kings Lynn has an interesting question here. It says, question, evolution. Everyone talks about how we evolved from bacteria or viruses that fell onto the planet. Is it possible that more than one type of bacteria or other various viruses had dropped onto Earth and evolved together with similar traits? Ooh, good one, Jonathan. Thank you. Chris?
Well, there is a theory, and it's called panspermia. And this is the idea that life originated from outside the confines of the Earth. And what happened was that the Earth formed a sort of propitious environment with the right amount of warmth. It was the right distance from the sun, and it had water, and it had effectively a way of shielding the surface of the planet, ozone, from ultraviolet rays, although the ozone came later because it made from oxygen. But the point is that the Earth was an ideal environment, and then something arrived from space which seeded life. Now, it's unlikely that that was a bacterium, although scientists have shown that bacteria can survive exposure to space. And there have been various experiments done showing that they could even survive being smashed into Earth in some kind of impactor. In other words, a meteor that turns into a meteorite when it slams into the Earth, if it had bacteria locked inside it. Scientists have done experiments, in fact, scientists in this country have done experiments on bacteria inside projectiles and shown that they could be slammed into the surface of the Earth, and as long as they didn't get boiled up too much, then they could potentially survive. Now, that means that if there were bacteria coming in from space, then maybe they could survive. What's more likely, though, is that life probably got started here of its own accord because the environment was right. And there was a guy who I was lucky enough to meet last year, and he works over at the University of California, San Diego, and his name is Jeffrey Bader, and he was a student with Stanley Miller. And Stanley Miller was a researcher who did some very famous so-called Miller experiments in the 60s and 70s. And what he did was to create this very interesting flask system where he had a load of water in a flask, and this flask had a tube coming off the top, which then went to a second flask that had two wires in it. They're at a separate distance apart, a short distance apart. And then the gas from that flask went to the bottom flask again in a sort of cycle. And what he did was to put some hydrogen in there, some nitrogen in there, and the water, and a bit of carbon dioxide. And he then boiled the water up to a very high temperature, and then turned on a very high voltage across those two wires, so they began to spark. It made lightning. And after he'd run the experiment for a few days, the water went brown. And this showed that he was clearly making something organic from the carbon and the nitrogen and the hydrogen and the water, all things which we think were present on the early Earth. And he analysed his resulting material that he made after running this experiment for a period of time. And what he found was that there were all kinds of organic molecules, including amino acids, the building blocks of proteins, the things that make our cells work, in that mixture. And so that shows that heat, a few simple chemicals, and some electricity could generate some of the building blocks of life. And why this is so poignant is that last year, Jeff Bader at UCSD went back to Stanley Miller's old experiments because Stanley Miller died and left all his old stuff and his gear from his laboratory to Jeff. And Jeff went through this material and found all the old vials from that experiment that Stanley Miller had done in the 50s and 60s. And he thought, well, what would modern science make of this? So he fed the results of those experiments into modern-day mass spectrometers, which are very sensitive pieces of equipment that can work out exactly what the chemical signatures of various things are. And he found tens, if not hundreds, of different compounds had been made by Stanley Miller's experiments. So the current theory, I think, of where life came from on Earth is probably less likely to be life coming from outer space. It could have been various proteins and chemicals that came in from outer space that helped to kickstart life here. But we think probably some warm little pool, hydrothermal vent, hot steam, some primitive gases and some lightning began to put together the building blocks of life that then eventually began to drive the chemical reactions that we see running in cells today. So we think life probably got started here of its own accord rather than came in from outside. But to be honest, we're never going to know, or at least not for a while anyway.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Good evening to Tony.
Good evening, Sue, my dear.
Ah, lovely to hear from you, Tony.
And you?
What's your question, my darling?
Right. I've seen quite a few things about the brain, and when they put them in, I think this is a scanner or something like that, they can see bits of the brain light up when it's stimulated by something. And I wondered, if you could tell us a little bit more about it, really, especially, say you've got a criminal, or whatever sort of criminal, could be a sex criminal or something with, nasty. Do bits light up that wouldn't light up on a normal person? And if so, we could zap that bit to stop them being like it.
Chris?
Only it were that simple.
Oh.
First of all, let's look at the question of brain scans and how they work.
Yeah.
This really has unleashed the power of science in a very big way, because before, the brain was this mysterious thing that we could only sort of prod and poke at and record with sticking needles into it from very small numbers of nerve cells, and really our understanding of the brain didn't really come alive until what's called functional imaging came to town. And functional imaging comes in a number of flavours. One way to do it is to use something called PET, which is positron emission tomography. And what you do is give people a tracer molecule, usually glucose, which has been labelled in such a way that when it's consumed by the brain, it breaks down by metabolism. The glucose decays because it's radioactive, and it gives rise to a positron. And the positron comes whizzing through the skull, and it can be picked up by a detector. And the theory is that if you give someone this radio-labelled glucose, then the bit of the brain that is most active doing a certain job will use more energy, and therefore more glucose will go to that area. And so if you record for long enough, you will see more activity, more breakdown, more radioactivity congregating in the area where the glucose is going than in other bits of the brain. And if you subtract one from the other, you can see which bit of the brain, therefore, is effectively lighting up when it's doing a certain job. So you put someone in a scanner, you get them doing some kind of fruitless, pointless task to get some kind of baseline activity, your control, or you just get them to think sweet thoughts to themselves, and you record what the activity profile of the brain is. And then you start getting them to do things. It might be moving an arm, it might be looking at certain types of pictures, it might be identifying colours, that kind of thing. And you then ask the brain, well, which bit is becoming more active? And by spotting where the radiation is coming from, you can pinpoint which bits of the brain are active. And that has helped scientists to understand a lot more about the localization of function in the brain. We had a fairly reasonable idea as to which bits of the brain, grossly speaking, did what. They were divided up over 100 years ago by a scientist called Brodmann, who divided the brain into more than 40 different regions, areas of Brodmann. They've all got numbers which do different jobs. But this approach enabled scientists to begin to understand in much more detail which bits selectively of the brain and which bits at once were involved and co-recruited to do certain jobs. Now, that's one way of doing it. Another way is to use something called functional magnetic resonance imaging, fMRI. And this is pretty similar, except that here, instead of using PET, what you're doing is you put someone in an MRI scanner, and this uses magnetic resonance imaging, so it's very, very high quality imaging, very high resolution, and you give people the task that you want them to do, and the scanner is able to look for where the brain is using oxygen. So in other words, where you get an enhancement of blood flow, because when the brain becomes active, it needs more energy, so it increases its blood flow to the bits of the brain that are becoming more active. Therefore, the blood flow goes up in that region, and therefore you can detect that. You can detect that increase in blood flow through the tissue using the MRI scanner, and therefore you can work out, again, at very high resolution, what bit of the brain is doing what job. And that means that then you can home in on certain bits of the brain that are involved in doing certain tasks. And again, this has added the ability to ask people to do complicated tasks in the scanner whilst looking very, very high detail at the surface of the brain and the interior of the brain as they do those tasks, and you can therefore work out which bits of the brain are involved in doing what. In terms of whether this could be used therapeutically, the answer is, well, it certainly helped us to identify which parts of the brain might be going wrong in certain conditions. So scientists are now putting people who have certain psychiatric conditions or neurological conditions into brain scanners and comparing the imaging from their brains with people who don't have that condition. And this is helping to show why people have certain conditions. People who have eating disorders show that certain parts of their brain, especially a part of the brain called the insula, which is where the brain seems to match up how behaviour relates to the impact that behaviour will have on the body. They seem to have a difference there if they have an eating disorder. People with obsessive-compulsive disorder. Scientists at Cambridge University showed a couple of years ago what actually is going on in the brain when people who have obsessive-compulsive disorder want to have their obsession. And they've homed in on a certain area which seems to become too active in people who have that condition. The next step, of course, is to then start saying, well, can we do anything about those conditions? Now, unfortunately, no one would probably support your wish to zap the bit of the brain that's doing that, because unfortunately bits of the brain that do bad things probably also do some good things. Yeah. So if you took them away altogether, then you'd leave the person disabled. What we want to do is to work out how to disable the bad behaviour, leaving the good bit of the brain intact. And so there are various drugs that can help with that. And so this kind of imaging, what you can do is to use drugs and put people on various medications and then do the tests again and see if this changes selectively the imaging profile, the bits of the brain that are being recruited, and see if you can make the person's brain profile, the imaging, look more like a normal brain profile. That would suggest that they're going to get a bit of relief from their symptoms, and that's how researchers are really pursuing this. They're not actually out there to zap bits of the brain, although occasionally there are certain conditions where removing bits of brain tissue can bring relief. And there are some instances where epilepsy, for example, cannot be properly controlled with drugs. So what doctors can do is to use imaging to work out which bit of the brain is triggering an epileptic seizure. And then they can go in with very high precision and remove just that piece, or take out just that tiny piece of the brain that's malfunctioning, and then the person doesn't have any fits anymore.
Tony, have you taken all that in?
Yes, I think I got it. He does explain so very well.
I know. That's why he's here. Tony, thank you very much for your question. Thank you. Dr. Chris, Charlie in Swaffham says that his wife brought a transistor radio for him so that he could listen to it in the garden. It's battery operated, and after having it for a week, he's found that the expected life of the batteries was 6 hours. How does this transistor radio go through these batteries so quickly, and does this reflect how much energy other electrical appliances use that we run from power points in the home? Chris?
Well, the electronics inside a radio will determine how much it consumes. In other words, there's a number of things that the radio is having to do. On the one hand, it's having to receive a radio signal. If it's got a display, which it has to light up, or a memory to hold some kind of memory of where the radio stations you've been listening to are on the dial, those things all consume memory. And then, of course, it's got to decode the signal, especially if it's a digital radio, and then it's got to turn it back into sound waves, and that means amplifying electrical signals to make them into bigger electrical signals that can then be used to move the speaker, and that speaker moves air, that becomes sound waves, and then you can hear it. So there's no such thing as a free lunch. So basically, if it's consuming batteries at those rates, that's because the electronics inside the radio are burning off the energy at that kind of rate. And yes, if you plug that in your home, then it would continue to use energy at that rate. And this is part of the problem, because many of the times we plug various appliances in and we just don't realise how much energy they're really using. The kettle, for example, you'd have to pedal your bike up a very steep hill for a very long time to burn off the same amount of energy, or even store the same amount of energy in a generator with your own body that it takes just to boil the water to make a cup of tea. So it's because we take energy for granted in the form of electricity that we've become really quite complacent about it. And I think sometimes actually having to see how much things use in the real world is a real eye-opener for me, certainly, when I do things like that.
We've got Curtis the cabbie from Royston, who says, bearing in mind coastal erosion, rising sea levels and global warming, where would you move your family for their long-term health and well-being?
Probably to the moon, I would think. No, I'm just joking. In fact, on this week's Naked Scientists, we'll be talking to a researcher from the University of Bristol who has just published a paper in the journal Science this week, in which he has been looking at the rate at which Greenland is losing ice. Now, Greenland has enough ice locked up on its surface to raise global sea levels by 7 metres if it all melts. Gosh. You might say, well, what's the worry there, because it's not melting? Well, it is, unfortunately, and it's melting at the rate of 273 cubic kilometres of ice every single year. And that's enough to raise the whole sea level around the whole world by 0.75 millimetres every year. So it's a very, very big problem. And if a whole of Greenland melts, which it could do, and sea level rises by 7 metres, that means most of the UK will be underwater. So the Pennines is a good place to go and live, because those are our high points. You could go there. The Lake District, I think, will still be above sea level, so that will be quite a sought-after location. And, of course, quite a bit of Scotland will, because it's highlands, will be above the water. But most of these places, especially Cambridgeshire, low-lying fens, no, all gone, I'm afraid.
How scary is that? All right, well, let's get to saliva now. Petra in Yarmouth says the human mouth produces about 1 litre of saliva a day. How and why do we produce it, and what purpose does it serve?
Well, it's mainly lubrication and protection. If you have, a good example, a good thing to think about is if you took your dry skin and just rub it over a surface, then you'll notice that friction builds up and it gets hot. If you, on the other hand, make the surface damp, there's much less friction. So saliva is partly there because that way it makes it easy for your tissues to move around, your tongue to move around your mouth, and for you to speak. It also makes it easy for you to get food in, chew food up, lubricate the food, break it up into bite-sized chunks, quite literally, and then swallow it, because you've got to propel boluses, chunks of food, from your mouth all the way down into your stomach. And if they were trying to rub against dry tissue, you can imagine the sticky mess. You'd soon get clogged up. So saliva is very important as a lubricant. And to help that happen, the body, when it makes saliva from your salivary glands, of which you have the parotid gland in front of your ear, your sublingual glands, the ones under your tongue, and your submandibular glands, the ones under your jawbone on each side, they also add to this watery mixture, which is actually made by filtering the water out of blood that flows through those glands. It also adds proteins, and one of those proteins is called mucin, and mucin is slimy. So that's your mucousy protein, which makes actually your saliva very slippery, which is why things slip down easily. Now, the other thing that saliva does is provide defence, and the other thing that your salivary glands add to it are antibodies. You have a class of antibody called IgA antibodies, and these are very good at soaking up or neutralising foreign invaders. So it's your first line of defence against food poisoning, bugs coming in from the outside world, viruses that you breathe in or inhale or put into your mouth on your fingers and things. So these antibodies are there to bind onto them and kill them. And there are also other defences in the form of enzymes, including one called lysozyme, that can break down bacteria. So saliva is very, very important because it protects you and lubricates you.
All right, let's go ahead to this one here. How much research is being done for alternative energy sources at the moment? Is there anything new that's come about?
Well, the answer is that there's a huge amount of effort to try to work out how we can avoid releasing CO2 into the atmosphere. Traditionally, underrepresented areas include solar energy, and that includes solar photovoltaics and also solar heating, putting energy into water. But also people are looking at where we actually put most of our CO2 into the atmosphere and why. And 40 or 50% of the average individual's emissions come from the place they live in, their home. So there's a big emphasis now on saying we could make a very big and dramatic difference to the amount of energy that we waste by insulating our homes properly and building more efficient houses and making the houses, the way in which we live in them, much more energy efficient. So that's where a lot of effort is being put, not just in terms of generating electricity, but making what we do with it and what we do with the energy that we have go further.
Sue has sent a text in here saying saliva. She's heard that baby's breath is so sweet compared to an adult's because they produce so much saliva, killing the bad breath bacteria. Is that true?
No, there's two reasons why babies smell different to adults. One is the teeth. Humans have teeth when they're older. Babies have fewer teeth or no teeth. And teeth provide a home for bacteria. And the stinky breath that people get is all down to bacteria. Bacteria break down things that we put into our mouths. They break down cells that shed from the surface of our mouth. They eat the food that we eat. And they break down other aspects of food, especially sulphurous components in food, and they turn out sulphur-containing chemicals which are stinky. So babies, because they have different spectrum of bacteria in their mouth because of the diet they eat, babies eat a lot of mother's milk, which suppresses bacteria, and also that will sustain a different range of bacteria than an adult diet. Therefore, the range of bacteria is different in babies than in adults. They don't have the stinky bacteria. They also have fewer places for those bacteria to hide because they don't have teeth. So those are the two main reasons.
All right, and lastly, Dave in Thurrock says, what is snot? Why do we produce it? And where does it come from?
There's a lovely article on thenakedscientist.com. If you look on our article section called why is snot green? And this answers this question, and it's one of the most popular articles we've ever published, actually. The reason we have snot, mucus, is that this is a substance which is basically a thick form of saliva which is produced in your nose and pharynx. And the idea is that it coats the mucous membrane, the surfaces and the linings of your nose, and it does two things. One, it protects the lining from particles that you breathe in. Because mucus is sticky, when you inhale particles, the air that you're inhaling spins in a circle like a Dyson vacuum cleaner, and this throws the dirt particles against the sticky layer and traps them. So it's a good way of trapping out dirt. It also does the same thing with bacteria and viruses, which helps to protect you and stop you getting infected. And that way, it also means that you're less likely for those particles to make their way down into your lungs, where they may play havoc, causing infections or more severe inflammation deeper down into the airways. So they do that, and it also provides a lubrication for your airways and a way in which you can clean your airways, because the snot is continuously being moved by what's called stereocilia, tiny hairs lining the airways which beat in register and push the mucus along towards the back of your throat, where you swallow it and the dirt that goes with it, and it cleans out your nose and throat and your lungs quite nicely.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.